At 93 meters tall, the Statue of Liberty stands as a historical benchmark for engineering ambition. Constructing it required a massive logistical effort for the late 19th century. After workers completed the copper and iron structure in France, they had to completely disassemble it, ship the pieces across the Atlantic aboard a steamboat for several weeks, and manually reassemble the entire figure on American soil. But compared to the monuments being built today, that scale feels almost quaint. We are now looking at structures that absolutely dwarf Liberty, peaking with the staggering 240-meter Statue of Unity in India. You cannot simply take 19th century building methods and scale them up. If you tried to build a 240-meter statue using solid cast bronze or traditional iron framing, the sheer weight of the materials would cause the entire structure to collapse under its own mass. To safely double and triple the heights of our monuments, engineers had to completely abandon traditional sculpting. They turned statue construction into an extreme test of architectural survival. The first major physical hurdle is keeping a structure over 100 meters tall standing upright in high winds and seismic zones without it buckling. India's 112-meter Statue of Belief, the tallest depiction of the Hindu god Shiva, provides a perfect case study for solving this exact stability problem. This cross-section shows how the innermost core tackles the massive weight. The center is a solid pillar of reinforced concrete, rooting the structure firmly. Surrounding that concrete is a rigid steel framework, acting as an impact-absorbing skeleton. The final layer consists of molded concrete pieces coated in copper and zinc. This multi-layered design solves the stability problem by abandoning the concept of a solid sculpture entirely. The structural core functions as a high-density armored bunker, while the human form acts as a thin, decorative facade. Even with a sturdy core, engineers face a cruel paradox. Traditional casting materials become catastrophically heavy as you build higher up. Japan's 120-meter Ushaku Daibutsu tackled this weight problem with a radical departure from traditional statue building. Instead of pouring a solid cast body, workers first erected a towering iron and steel column to serve as the structural backbone. They then divided the vertical height of the planned body into 20 distinct horizontal tiers. This diagram illustrates what engineers call the curtain wall method. Lightweight bronze blocks were pre-assembled on the ground and then hung onto the steel frame tier by tier. This leaves the entire inside of the statue completely hollow. By abandoning solid mass and borrowing hollow cladding techniques directly from high-rise skyscraper construction, engineers safely pushed past the 100-meter height threshold. But stripping away mass introduces a severe logistical bottleneck. What happens when your remaining building materials are still physically too heavy for your construction cranes to lift? Take Indonesia's 122-meter Garuda Wisnu Kencana. To capture its highly intricate details, the structure was divided into 700 massive modules and fabricated in a specialized factory 800 kilometers away. Transporting those modules was difficult enough, but upon arriving on site, the crews hit a breaking point. The massive pieces were simply too heavy for the cranes to safely hoist into the air. The solution was extreme modularity. Crews sliced those 700 modules down into 1,500 micropieces, lifting them one by one and carefully reassembling the puzzle mid-air. That slow, methodical assembly stands in stark contrast to the aggressive 5-year timeline of the 240-meter Statue of Unity. That massive project required incredible national coordination, including a movement that collected and melted down farming equipment from willing donors to source enough iron for the skeleton. Overcoming crane weight limits meant completely rethinking the supply chain. Monument construction is now an exercise in highly coordinated microassembly. Skyscraper curtain walls, modular factory fabrication, and multi-layered impact cores have effectively removed the historical height limits on what we can build. But those physical solutions have only fueled even wilder ambitions, leading to massive, stalled proposals like the 212-meter Shiv Smarak project. The scope of the Shiv Smarak is so large that it requires constructing a custom artificial island off the coast of Mumbai just to support the sheer weight of the statue and its museum complex. Then there's the proposed 252-meter Statue of Lord Rama, a plan that pushes our conceptual ambition even further upward. Yet both of these projects have faced intense delays. While the engineering math checks out on paper, the practical, real-world logistics of actually sourcing and funding these megastructures are struggling to keep pace. Today's megastatues serve as cultural landmarks, but their existence proves that building a monument now requires the same industrial-scale logistics as a deep-water oil rig or a skyscraper. They represent the point where art meets the absolute edge of what our machinery can lift.